Hello everyone, this is Cameron Snow with Danomics.com. In this webinar, we're going to be discussing performing mineral inversion at scale. And this is something that I think can be a real game changer when applied at scale. I think it offers a superior solution to some of the traditional methods. So we're going to go through that, and then at the end I'm going to show you how at Danomics we can overcome some of the traditional difficulties that have been discussed when talking about mineral inversion at scale. So in this webinar, we are going to start off by discussing why we use mineral inversion in the first place and what it is. Then we're going to talk about the basic theory behind mineral inversion. This will be at a very high level, and if you'd like more information on this, we're also going to be releasing some educational videos later in the week that will go into mineral inversion in detail. Then we're going to discuss how mineral inversion can really be a game changer when performed at scale. And then I'm going to talk about how the Danomics platform can help you implement this type of analysis. So when it comes to petrophysics, we often think about the workflow that we're using, and traditionally what has been used is what's called a deterministic workflow. And this has really been the foundation of petrophysical analyses for quite a while. And it's actually an excellent starting place for performing any type of analysis. All the equations that you'll encounter are relatively easy to work through, and this is something that you could replicate in a spreadsheet or in any system of equations, or you could even calculate it by hand in most cases. And it provides pretty good results, especially if you have relatively straightforward lithologies and your units are relatively homogeneous. However, if you're working in more complex systems, you may need a slightly more sophisticated workflow. And this has taken many petrophysicists to performing what's called a probabilistic workflow. And really the difference here is that instead of using something like a traditional density porosity or sonic porosity, we use a mineral inversion based porosity. And this alleviates some of the challenges associated with having complex and mixed lithologies. And in general, people believe that this gives us a better answer when performed correctly. So, with that background, let's jump into what a mineral inversion is and why we use it. So if we think about a standard porosity calculation, let's say something like a density porosity, we have this equation here where the porosity is equal to our matrix density minus the density from our log divided by the matrix density minus the row fluid. Very, very straightforward equation here. And when we apply it, so let's say we have an example system like this one here to our left, we need to, we need to set our parameters here. So our geoscientist has given us a top of the zone and the base of the zone. Here we have our bulk density log, and now we need to provide a row matrix. So in this case, if we want to analyze our sandstone, we might set our row matrix at 2.65. This would give us a correct answer for our sandstone unit, because this does have a matrix density of 2.65. However, we would be underestimating the porosity for our limestone unit and our calcite cemented sandstone unit here. And that should be clear from this equation. We're just using the wrong matrix density for those lithologies. So if we change that up and say, oh, well, let's use the correct matrix density for our limestone. Well, that would be a matrix density of 2.71. Now in this case, we're going to be correct for our assessment of porosity in the limestone, but we're going to be overestimating our porosity in our sandstone and in our calcite cemented sandstone. Well, what we would really like to do is we would like to have, our row matrix vary according to the lithology. So when we're in our limestone, we'd like to use a row matrix of 2.71. When we're in the sandstone, we'd like to use a 2.65. And when we're in this calcite cemented sandstone, we'd like to use something that lies in between. And we would call this type of assessment, we would call that a grain density, which leads us to this equation. So now, instead of using a fixed row matrix, we're using a variable grain density. Now, what you may be thinking to yourselves is, oh, this is simple. I could just add another formation top here, and then I could, select, a 2.71 in this unit, and a 2.65 in this unit, and something different here. Well, so let's think about that. So first of all, down here in this unit, what are you going to use? It needs to be between 2.65 and 2.71, but where should that be? Well, if we can calculate a grain density, then we know what this should be. So grain density allows us to overcome the difficulty associated with that. And I mentioned earlier that perhaps you could just pick additional tops here. Well, that works fine if you only have, a couple of extra tops to pick. But what happens if you have, a lot of interbedded sandstone and limestone instead of just 2 units? Well, that doesn't scale up. All of a sudden you have to pick many, many tops, and you'd have to do this for many, many wells. Also, are you going to be able to readily identify the difference between this sandstone and this calcite cemented sandstone? Their log signature could be very similar, if you're only looking at something like a gamma ray log in that case. And using a grain density methodology will allow us to overcome that difficulty as well. But let's try to quantify this a little bit. So here we are going to be looking at 2 toy models. Now, I just want you to put aside that, yes, it is very unlikely that we are going to have something that we know is exactly 65% quartz and 35% calcite, and that maybe that's too simple of a system. But I think these toy models are useful. So, let's say you just took a quick look at your log and you said, oh, this is a clean sand. My matrix density should be 2.65 grams per cc. Oh, I can see my log is reading a value of 2.58. You can do that quick calculation using the density porosity equation, and you're going to get an answer of 4.2%. Okay, well, maybe we then decide to calculate a row grain density. We perform our mineral inversion, we calculate a row grain density, and we get that grain density comes out to be 2.67 grams per cc, so slightly higher. We have the same bulk density that we measured on our logs, and this would then tell us that our porosity is calculated using that grain density is 5.5%. This is a very material difference. This is a difference of 33% in this case. And if you think about how you might set cutoffs, to analyze something for net reservoir or net pay, you may set that cutoff at, let's say, 5%. And if you did that in this case, that's the difference between flagging something as reservoir and non-reservoir quality rock. Okay, so that's a very simple example. Let's look at another one here. So in scenario 2, we have an organic shale. And it's a very complex lithology. We got some kerogen and pyrite, calcite, quartz, and clay. So my first question is, how do you even know what the matrix density should be in this case? You may say, okay, maybe that's something like 2.75, because we know that, we got some pyrite in the system that's high density. We know our clays are higher density. Let's use that. We then look at our, bulk density log, and we calculate a density porosity of around 9.7% when we use that 2.75 for our matrix density. However, if we go through the mineral inversion, it's going to tell us that our grain density is around 2.69, which tells us that in this case, our porosity is actually substantially lower. It's actually around 6.5%. And if you overestimate that porosity, it may lead you to, some operational decisions that you're not going to be, happy with after the fact. You may say, my recovery factor is lower than I expected. Maybe that means we can drill more wells in this area. When actually what's the case is that your in-place volumes are just lower because the porosity is not as good as you thought it was. And it's this type of benefit that performing a mineral inversion to determine a grain density provides us. It allows us to have a more nuanced and sophisticated look at the porosity. So this is a set of key takeaways, and this is something that I'm going to repeat multiple times during the talk. Mineral inversion provides us with a better solution to porosity most of the time. The reasons for this is we are calculating a variable grain density instead of setting a fixed parameter for a zone. So we're able to, to be more granular in our analysis. So that allows us to handle these mixed lithology systems where we have, interbedded sand, shells, and limestones without having to endlessly subdivide. And it provides us a way of, calculating that grain density in complex lithologies, which otherwise would be very difficult to set unless you have, some core to help guide you to setting that parameter. So those are some of the reasons why we use inversion. Now I want to cover some of the basic theory behind mineral inversion. And I'm going to cover this at a very high level, and it'll probably be unsatisfactory to some of you. And if that's the case, please watch our educational videos on the theory behind mineral inversion, where we go into a lot more detail on that. So basically, what is the theory of mineral inversion? It basically involves a little bit of matrix math, where you would say, if you have a matrix of our mineral properties, and you know the volume of those mineral properties, you would be able to calculate the log response exactly. And so let's look at a simple example of that. So let's say we have a system with 3 minerals: quartz, calcite, and dolomite. If we know the density of quartz, calcite, and dolomite, and we know the volume of quartz, calcite, and dolomite, we should be able to calculate exactly what the bulk density of our rock is via this simple equation. We could do the exact same thing with a PE log. If we know the PE log values of quartz, calcite, and dolomite, and we know the volumes of quartz, calcite, and dolomite, we should calculate what the photoelectric response of our well log should be. And so, so that's a pretty bold statement, but it is one that I think you can, prove true to yourself by looking at just, extremely simple examples like this. If you know all the mineral components, if you knew all their properties, and you knew the volume of all of those, you should be able to calculate what the well logs should be. Therefore, logically thinking, we know that we can rearrange this equation. So if we know the properties of all of our minerals, and we know what the log response is, we should be able to calculate what the volume of each mineral is. And you could see how you would start to do that from these simple examples here. In this case, we've got, 3 unknowns, our volume of quartz, calcite, and dolomite, and we've got 2 equations here. So you could see if we had a third equation, so let's say we also set up the exact same equation for the neutron response, you could see how we could rearrange those equations to solve for our 3 unknowns in this case. And that is the foundation of how inversion works. Now, of course, life isn't quite that simple. So we have to be a little more sophisticated in our analysis, but that is basically how it works. We have a system of equations, and we are solving for a system of unknowns, and the most efficient way to do this is through some matrix math to get the solution. So, as I said, it needs to be a little more complicated here. So first of all, we rearrange our equations here. So we're now solving for the volume of our minerals. We apply some basic constraints. So we know the volume of each mineral has to be, greater than or equal to 0 and less than or equal to 1. We know that our log response isn't perfect. So, we need to decide how much that varies by, and then we can try to minimize a difference between our actual log and our predicted log, weighted by the uncertainty in the value of our log measurements, and we call that incoherence. So if we have our incoherence for logs A, B, C, etc., we want to minimize for this total incoherence, and we do that via application of a solver. So that is, a basic computational technique, and that is what underlies the mineral inversion model in almost every software. So what I'll say is, regardless of the software that you have access to, it's going to be some variation on this basic method. However, there's going to be some differences in the defaults that are suggested for use. There's going to be differences on how we weight for uncertainty. There may be some differences on how we perform that minimization, and some differences in how we handle constraints. And in a lot of cases, this is not something that is well publicized or documented, and a lot of times we consider this to be trade secret. However, what you need to know is, at the end of the day, you are solving to minimize the error between your actual and your observed logs, subject to some number of constraints on your equations. So that's what we're doing at the end of the day. Within Danomics, I just want to show you what the mineral inversion module looks like. So we have our mineral component matrix here. We have our log matrix here, and what we're trying to represent here is this is the volume of minerals that we are solving for. And we provide you with a layout where we show you the resultant mineral volumes. We show you the grain density that gets calculated from those mineral volumes, the sum of the fluids that gives us our total porosity, and then we show you the actual and predicted logs that come out of the mineral inversion as a means to QC the accuracy of the model. And within our software, we have set it up so you can essentially visualize that equation. So here it is laid out on one, kind of in one row, where we have our component matrix C. We have the volumes of minerals here that we're solving for, and we have our log responses laid out here. So that is that basic matrix math of C times V equals L. That's how we set that out within Danomics. And essentially, from a practical point of view, what it is we do is we assign a mineral mix and we set out the properties for those minerals. And then we go through and we customize that mineral mix on a zone by zone basis as necessary. So that is the basic theory at a very high level. Like I said, if you want to go deeper into that, check out our educational videos on our YouTube channel, and I'll actually be posting those on LinkedIn as well, so you can find them there. But now I want to go into why I think mineral inversion should be applied at scale. So mineral inversion, it provides a better answer on a single well, and I believe that the benefits of doing it at scale really multiply. But a lot of people will say, can this really be used at scale? What a lot of people will say is that you can't do mineral inversion at scale, and they'll tell you this is some type of Sisyphean task where you will forever be pushing the boulder up the mountain. And I'm here to tell you this is not the case. So the argument that I hear a lot of people make is simply that performing mineral inversion is too complicated for G&G staff to do. I believe, first of all, that most geoscientists can understand mineral inversion. They may not be able to perform this calculation on paper. They may not be able to program it up themselves, but I certainly believe they can understand it at a high enough level to be able to effectively perform mineral inversion. It's just that traditionally they have been forced into using softwares that don't have this capability, and part of that is because when looking at legacy conventional systems, maybe we didn't need that level of sophistication in our analysis. You'll also have people tell you that mineral inversion is simply too slow to use on large well counts, that due to the process of having to apply a solver to this, it's just too computationally intense and it runs too slow. And the follow on to that is that the software packages that are available on the market, yes, you can run mineral inversion on 1 well, 10 wells, maybe even 100, but you start to get beyond that and it really doesn't scale up. The software crashes, the compute times are too long, and so it's not a scalable solution. And and then you'll have people that will also say that, hey, mineral inversion is great. However, the parameters that go into that mineral inversion, they're not constant. They vary regionally, and that's just an obstacle to performing this analysis at scale. First of all, I'm just going to discount this first argument. I believe that G&G staff, when given the proper tools, and a little bit of training, can apply these models effectively. I don't think this is a process that has to live with the petrophysicist. And then I am going to go through and I'm going to, lay out why I believe that, if you have the right software solution, it's not too slow on large well counts, that it can be performed at scales, and that when you have the right tools, that you can overcome the challenges associated with parameters that vary regionally. So, why does mineral inversion, offer potentially game-changing results? Well, the first thing is, I think, it allows us to set mineral models and not a matrix density. I will go through why I think that this is important, and why I think that we are actually better at setting mineral models than we are at evaluating what a matrix density should be for a system. As I mentioned before, it handles this mixed lithology problem. So mineral inversion helps us overcome this, and this is crucial when you are looking at things at scale. And it handles complex and variable lithologies better than traditional methods as well. So let's start off with the mineral models. I believe that when we are setting a mineral model, we are better informed about the inputs. So that's one of my theses here. And first of all, I'll start off by saying that most systems have a very limited number of mineral constituents. If you think about your average siliciclastic system, you're probably going to have quartz, calcite, and clay. And then in some circumstances, you're going to have maybe some kerogen and associated pyrite. And in other circumstances, maybe you'll have something like an orthoclase or some type of potassium feldspar in there. So in most cases, 5 to 6 mineral constituents will make up 95 to 99% of your rock. And you're just going to have some other trace minerals that are in there. So I think most of these systems can be modeled quite effectively with a limited number of mineral constituents. Second of all, as I'm showing here in the diagram on the right, we have mudlogs on nearly every well that gets drilled, or at least a large number of wells. And the mudlogger goes through and they provide a description of the mineralogy. They tell us if they see quartz, clay minerals, things like pyrite. They'll do acid tests to see if there is calcite present in a sample. So they can provide us with a lot of information that helps us establish our mineral model. We can also, collect cuttings and perform XRD analysis on those, and that's quite a cheap process, and that provides us with a list of the minerals, so we can then, set our mineral model based on something that we have actually measured from the well. And if we have core or some larger cutting chips, we can actually make thin sections of those and perform a proper petrographic analysis to help us set the mineral model. Whereas if we contrast that with trying to set a row matrix value, in order to do that, what we need to do is we need to take our core, our cuttings, and we need to measure the grain density. Now, this is something that can easily be done, but it is a more expensive process than some of the methods I have outlined above. So, that is, I think quite important, because now, we are setting something that the geoscientists should have a very good understanding of. They should have a very good understanding of the potential mineral compositions of our rock, and that is something that should be much easier established than the grain density. Okay, so what about mixed lithology systems? In many cases, we have mixed lithology, such as what's shown here on the right, which is a schematic from the Bone Spring formation in the Delaware Basin. And if you had to set a matrix density on this, you're really held hostage to the resolution of your tops. So, okay, maybe if you want to, analyze your first Bone Spring sands, you could set that and get it right here, and maybe you're going to be, pretty much correct for maybe your second bone as well. But you're going to be wrong when it comes to, any of these interbedded carbonates. You're going to be wrong in, the shells. And if you have, some sands that have maybe a more nuanced lithology than just being pure quartz, you're going to be incorrect in those as well. Now, of course, you could subdivide. You could go through and you could pick tops at the top and base of each of these. However, that is not scalable as you move up to larger and larger well counts. And so, because a mineral model can handle multiple lithologies, it can handle many rock types, it means that we can get away from this endless subdivision. So once again, if we think about that simple starting mineral model that you may use, that's quartz, calcite, clay, kerogen, and pyrite, let's say, it's going to be able to effectively handle this stratigraphy nearly from top to bottom. So that means that you just need to pick a top and a base and let your mineral model do the work for you, as opposed to having to endlessly subdivide these units. Mineral models, when set up correctly, can also handle the type of subtle changes that may otherwise be quite hard to correlate out. So we look down here in the third bone sands, we see there's a little bit of complexity there. Well, if we have that complexity accounted for in our mineral model, we don't have to worry about trying to split out many additional subunits, which may not even be really possible to do consistently across a play. Now, if you're working with a small number of wells, sure, subdividing is possible, but as you scale up, this starts to become, really difficult from a tops management perspective. And the more and more complexity that you try to account for, you're really going to start to open yourself up to having some inconsistency. So really, unless you have, a simple system, you're not going to be able to fully address the issue through increasing the density of your zonations, which is another, powerful argument for, why mineral inversion provides a superior answer. Okay, and one of the things that I believe is that opportunity is found within complexity. And there are a number of ways that complexity can arise. One of those in the subsurface is due to depositional setting. So if we look at this block diagram here to the right, let's say you're sitting on the beach and you're looking seaward. Well, what are you going to see? You're going to see that you're sitting on a clean sandstone, and as you progressively go further offshore, you go from your upper shore face to your lower shore face to some distal sands out into the offshore area. And as you are traversing across that area, you are going to go from these clean sands to progressively shalier sands out into the shales, and the grain density is going to reflect this. You are going to have variation in your grain density across the system. So that is one thing that we need to account for, and this is just a very simple sand shell system in this case. And I would argue that you're probably not going to be able to address this through additional zonation, additional subdivision of your tops. The reason why is this is a lateral change across the system, not a vertical change. So, all of this is happening at the same geological time. So this is really something that is more in the realm of sequence stratigraphy than you would get from a lithological type of correlation. So, within the same zone, you're going to have, upper shore face, lower shore face, and distal facies. Now, what's interesting is as you go across this, yes, the lithology is starting to change, and the grain density is changing, but the mineral model is not changing. So that mineral model and the inversion that we're performing can fully account for the diversity that we see in this system. And if you want to see a good example of this, I would say let's go up to the Powder River Basin. There, traditionally the Parkman sandstone, it was drilled in the upper shore face depositional facies, where you have a nice high quality sand there, and there are lots of old vertical producers. However, as companies started to get more sophisticated in their analyses and as horizontal drilling techniques became available, they were able to identify potential in the lower shore face sands. And part of identifying that potential is having a more nuanced view of the grain density, so you can realize that you actually have higher porosities than you would otherwise calculate, which leads you to realize that the saturation profile is better, which allowed this to be a play that has flourished here in the past few years. So that's a good example of a play that was able to be better understood through performing mineral inversion. Okay, so another area where there is an abundance of complexity is within organic mudstone. So, as we're looking at these organic shales that, have really been, drilled substantially in the last 10 years, these are not simple systems. Now, it may be very easy to correlate these systems out across a basin. However, there are a lot of changes that go on. And if we look at these different photomicrographs of organic shales, and these are all from the same play, we can see that there is a lot of variability in here. We have in some areas more quartz-rich organic shales versus other areas that are more calcite rich. In some areas we have associated pyrites, we have some other trace minerals that maybe need to be accounted for. Once again, our mineral model can handle this. These mudstones, they are far more spatially diverse than their conventional brethren in many cases, with respect to things like their grain density. However, the mineral model, is significantly more stable. And that means that we can use this technique once again to get a more sophisticated answer, so we can really crack the code there with how these things vary across a play. So it's one of those things you need to keep in mind that even when rocks correlate across very well, and they have similar features with respect to things like their gamma ray and their resistivity response, there is still potential for there to be a lot of differences with everything from the mineralogy, which then affects the grain densities, to to even things like their geomechanical properties. And so a mineral inversion can help us understand this better. Okay, so once again, the same three key takeaways. Mineral inversion provides us with a better solution for porosity, and that's because we're using this variable grain density curve, which allows us to better handle mixed lithologies and complex lithologies, without having to go in and make changes on a well by well basis, or without having to endlessly subdivide our well logs into finer and finer zonations. So that is a really those are the key takeaways in my opinion. And I would argue that if you are looking for new potential under your acreage, the only way you're going to find it is by diving into some of these more complex lithologies and seeing if the next sweet spot is actually being hidden by a little bit of complexity. So what is it that we can uncover by taking a more nuanced or a more sophisticated look at your acreage? And I think that is very important, when prospecting outside the core part of established plays. Okay, so now I want to go into how Danomics can help you scale up, in analyses that utilize mineral inversion. So we go back to the list of doubts. that people have. So first of all, like I said, I think that when, given the right tools and a little bit of information, G&G staff are more than capable of applying mineral inversion models. So we're just going to wipe that off the slate. But now I'm going to go through and discuss some of what we've done at Danomics to address the other issues. So is the software too slow to perform mineral inversion? Not with Danomics. We knew that speed was important, and we have done a couple of things to make our software 30 to 50 times faster than our competitors. In some recent benchmarking, we were able to run through 685 wells that used a full mineral inversion in approximately 12 minutes. And I think this offers a huge advantage because it means that you're now able to iterate through, you're able to experiment. So you can look at 3, 4, 5 different scenarios, in a reasonable period of time. Whereas if you look at something, where instead of taking 12 minutes, it takes 12 hours, you're going to not be able to iterate. You're going to run it once and you're going to end up having to go with the first answer that you get out as opposed to running it multiple times. So, I think we are able to overcome the limitations on speed. And the way we did that was through a combination of utilizing the cloud and utilizing, modern computational techniques. So we can, scratch that off the list. So what about, is the software actually architected in a way that allows you to run mineral inversion at scale? So a lot of people have come to us and said, well, I've traditionally used, a legacy software package, something like a TechLog or an IP. And when I try to run 1,000 wells through it, I run into all sorts of errors. The software crashes. It never finishes the run. I have to split it up into many, many runs. How is your software different? Well, we have real life customer projects that they are running with more than 10,000 wells. And the reason they're able to do that is we designed the software specifically with scale in mind. That's one of the reasons we decided to build out on the cloud, is so we could take advantage of cloud computing to enable this. But it's not just that. It's not just about having our software on the cloud that enables to do it. We also spent a lot of time on the data management aspect of this, which is just as important as compute power. Because if you don't have robust solutions for curve aliasing, data conditioning, etc., you're not going to be able to run mineral inversion at scale. And that's one of the areas where Danomics really excels, is in the data management aspect. So we can wipe that off the list as well. And now we come to, for what many people would say is the most formidable challenge, which is when we're doing petrophysical analyses at scale, we know that many of these parameters vary regionally. And I completely agree with that. Of course, these properties vary across a play. If we look at something like this map where we're showing a couple of different properties here, we can see that these properties do vary substantially across a play. So what varies? We can have things like maturity, formation salinity, the type of hydrocarbons, and the things like gas-oil ratio. When we're performing a mineral inversion, we need to know the sonic and resistivity values of things like our clay minerals, which can vary across a play with compaction. Things like kerogen density can vary across a play, and that's related to things like the thermal maturity. So, we need to understand that. And there's, many properties that you can vary across a play. And this is something that we have put a lot of thought into at Danomics. And, so a lot of packages, especially legacy petrophysical packages, they don't have spatial awareness built in. They don't have built-in mapping, and that means you're really looking at things in isolation. At Danomics, that's been one of the things we've been concerned with from the start. So, how do we handle this spatial variability? Well, many properties, their spatial variation can be represented via mapping. And a lot of times these maps can be generated from taking a statistical look at the well logs and then making maps of properties. So within the Danomics platform, we have built-in mapping, and then we allow you to extrapolate values off of those maps. So let's say, for example, here we had a map of maturity values here in the Powder River Basin. Well, if you load this map up into the software or generate it within the software from something like Core Data, you can then populate the maturity parameters on a zone-by-zone basis based on the intersection of the wellbore and the surface. So now anything that you can map, you can use to inform your petrophysics. So if you think about something relevant to the mineral inversion, like the sonic value of your clay, which is affected by compaction, now we can go through and we can, quite simply calculate, what the clay value of our, or what the sonic value of our clays are, and we can generate a map off of that, and then we can use that map to inform our mineral inversion. So that allows us to accommodate for that type of spatial variability. We can do the same thing with the resistivity of our clay. We can do the same thing with kerogen density, and so on. And one of the beautiful things about this is because we're doing this from a map, QC is inherently built into the process. You can visually assess, the results. Okay, in terms of the physical process of how we actually do this, well, you look at your parameter menu, you will click on the settings for this parameter, and you'll say, all right, instead of typing in a value into a parameter box, we'll now pull that value from a map, and that will now populate our petrophysics. So it's really kind of a click of a button to be able to perform that type of analysis. However, you're not just limited to grids in Danomics. We also have what we call parameter interpolation, where essentially, if you have interpreted multiple wells, you can use those hand-interpreted values to populate parameters from other values. So what we do is, let's say here in this simple example, you have interpreted these 3 wells. We can triangulate a solution for any property for this 4th well, and we can do this, of course, over and over, where we calculate this triangulation multiple times and use that to build up an interpretation from the ground up. So this is useful when you often may not have the necessary density of data from the start to make a grid. Well, we can build this interpretation from the ground up. So once again, within Danomics, what do? You tell your parameter that you want to build out a spatial table, and as you build up the interpretation, it will start triangulating a solution here and using that to populate your petrophysics. And if you want to add another manually interpreted point, you can easily do that via this menu, which means that you can make your analysis as granular as needed. So I find this technique is often quite useful for properties where they kind of vary in a systematic way across the field. So I think that's a great way to perform a more sophisticated analysis and build it up as you continue to perform additional manual interpretations. Okay, the third way that we handle variability in Danomics is through something that we call parameter remapping. So what parameter remapping does is, in the background, we're generating a lot of statistics. We then identify how you choose parameters on that statistical distribution, and then we will map those parameters to a target well. The best way to visualize this is through a simple example. So in this example, I have a key well where I've gone through and I've manually interpreted, let's say, clay endpoints for my gamma ray. And you can see I've picked those here. And then our parameter remapping looks at how I've picked these parameters relative to our statistical distribution. And it automatically, assesses that in our target well. And you can see that it's able to handle some of the subtle variation that arises due to differences in our well logs. So that is another process via which we can handle spatial variability across a play. So now I think with hopefully what I've shown you there, we can go and say that it is quite possible to handle that regional variability. So now we've addressed the issues due to complexity. We've addressed the issues due to speed and scalability, and actually being able to get the necessary parameters into our petrophysical assessment. So hopefully I've convinced you that doing this type of analysis is possible if you have the right software solution. So once again, just to summarize this, mineral inversion, I think, offers a superior solution because it allows you to handle mixed lithologies without subdivision. It allows you to handle these variable and complex lithologies, and it allows us to establish a mineral model which we often have a much better grasp on than we would if we were trying to actually set a matrix density zone by zone. And a lot of the traditional arguments against using mineral inversion at scale are simply not valid. I think G staff, so your geoscientists, are perfectly capable of performing a mineral inversion, assuming that the software is designed in a way that they can intuitively perform the parameter entry. By utilizing smart algorithms and cloud computing, you're able to perform mineral inversion faster, and you're able to perform it at scale. And that's something that, because Danomics is a new software, we were able to benefit from the previous 30 years of hindsight, so that we were able to build out a solution that addresses the problems that interpreters are running into now. We also recognize that understanding spatial variability and accounting for that is important, which is why we've built a number of methods into the software that allow us to account for that spatial variability. Okay, well, thank you for your time on this. If you would like to learn more, we're posting a number of webinars and educational videos on our website. So you can go to www.danomics.com. Also, while you're there, if you would like to do a trial of our software, you can actually create yourself an account for free and get started today. Just click on the Create Account button on the center right-hand side of the website. Or if you would like to schedule a demo of the software and walk through it in detail, feel free to send me an email at csnow@danomics.com or message me on LinkedIn, and we can get something scheduled so you can see Danomics in action for yourself. Thank you. Goodbye.